with that, I'd like to invite our first speaker, Erik, who will be presenting on using Maple and quantum chemistry toolbox for nanoelectronics. So welcome, Erik, and please share your screen now.
Well, thank you very much, and I will get that started. Hopefully, let's see here. And screen share, let's get from the beginning. And of course, it did the other way, so we have to stop that. All right. Never does it the right way the first time.
Looks good.
Everything? Yeah. All righty. Welcome, everybody. I guess since I'm starting out, I'll just introduce myself. I'm Professor Erik from Rowan University. That's a growing research university in the state of New Jersey. And I'm here today to just talk about my work, which is a combination of nanoelectronics and Maple, as well as the quantum chemistry toolbox for this purpose, right? And I kind of want to just give a little bit of motivation for why I study something like this. Well, the issue you might have heard of, especially if you've been following stuff like the CHIPS Act in the US lately and the various international shortages that have been resulting in electronics lately, is, well, traditional electronics are kind of reaching a theoretical and practical limit. There's some data from the roadmap of semiconductor devices. Well, based on the famous Moore's law, it's been expected these devices will become faster and better every 2 years. Although even by some metrics, not beyond just adding more transistors to a silicon chip, the performance is starting to fall off. And if anyone's been following NVIDIA's work lately, you know that they've been melting power cables and stuff with all the thermal problems they've been having, because silicon's not the best conductor in the world in terms of heat. So it tends to produce a lot of it. That's not easy to get rid of it when you pack a ton more and more transistors in a smaller and smaller space. Doing so is also getting increasingly expensive, with costs ranging into the billions of dollars for one plant and going ever upward as more and more people try to get into this space. So what my research focuses on is, well, making the next generation of devices, what will succeed the current packing more transistors into silicon model. And there's a lot of these devices, broadly described as nanoelectronic. The one type that I tend to focus on the most these days is the molecular electronic, which is not really a new idea. It's actually quite old. First popularized by Ratner and Avram and Ratner in 1974. There's a nice little picture of it right there, their original concept. And the idea is, instead of using a transistor etched into silicon or a switch etched into silicon, you put a molecule between two electrodes, usually a metal, although I have seen at least one case where they also use silicon for that. And then you simply slot in that new device into the role of a traditional device, right? You can plug it in, the idea being you could plug it into a circuit board and gain some efficiencies, or use a unique quantum property, say, for example, the electronic spin, in order to get a smaller, more compact, more efficient device, or increasingly things like a quantum sensor, or a quantum-based computing device. Now, old field, been around for a while. Why haven't we seen more of it? There are a couple applications. In fact, I believe there's a new startup called Roswell Biotech, which is using one for a sensor these recently. But the problem with these devices is twofold. One, they're hard to treat, specifically with theory, which is what I'm going to talk about today, on top of being difficult to make experimentally, as with many other nanoelectronic or nanoscale things. So just to show a quick example of an older problem in this area is, if you take a look here, you can see in the blue is an experiment for one of these devices where you're increasing the length of the device and conductance is falling, by orders of magnitude as the device length goes up. Experiments in blue. Your common theory, in this case based on density functional theory, is in black. And although this is a very good group and they did excellent work here, they still managed to get 2 orders of magnitude difference with the standard theory. And they've managed to make a nice correction to that, which they call the sigma correction, which actually mostly fixes that. And that error they found was based on errors in the electronic structure theory, or the description of the electrons that move around these atoms right here. And so my work focuses on fixing this error wherever it shows up. It's not the only error. It's sometimes not the most important error. Sometimes it is, depends on the problem. But it's something that I have a lot of experience with, and is something that is very tractable with something like Maple Quantum Chemistry Toolbox, because what my research focuses on is taking better electronic structure theories, say as we call them 2-electron theories instead of the traditional 1-electron theories, and using formalisms like my NEGF-RDM formalism to get new transport equations, in this case, the non-equilibrium Green's function, or NEGF. So I'm not going to go into a lot of detail on this because that's not really the focus of this talk, but I kind of wanted to show an overall scheme. Our goal is to use something to get our 2-electron theory, connect that through our transport equations in order to calculate charge transport in electronics. And all of the code to do this, especially this NEGF-RDM, is available on GitHub through the Rowan University Quantum Transport Program. So that's what you'll be looking at for the next little bit. Now, just to show an older result and to show that this actually does work, I have some results from 2 of my students, now both graduated. They were both undergraduates in my group a few years ago. And they looked at a simple biphenyl system with a very simple electrode. And they compared it to another very similar system to try to look at, hey, do we see current through here for this kind of molecule sitting on top of 2 gold electrodes, sort of a gap between the two. And they found that, well, we were actually able to get very close to experiment within an order of magnitude with our methodologies, whereas our attempts to reproduce other methodologies and other methodologies themselves, despite using a bigger model with better electrodes, were very far off, on the orders of magnitude level. And again, this is just illustrative. There's other things to consider, but we feel like this showed our methods work pretty well, and we are capturing extra electron effects that even other methods as we calculate are not. And just adding electrodes, for example, doesn't fix your problem in this case. You do need to get both the improved description of your system and the improved electrons. Now, how does that apply to Maple, which is kind of the meat of this talk? Well, in 2019, Maple and RDM Chem LLC released the Quantum Chemistry Toolbox, which has density functional theory, wave function, and these unique reduced density matrix methods, which really you can't find almost anywhere else, right? And definitely it's probably the best implementation of several of them, including the one I'm going to show here today. And this lets you do quantum chemistry calculations with Maple worksheets. And what we've done is pair this toolbox with our quantum chemistry code to be able to calculate non-equilibrium Green's functions, reduced density matrix, and DFT, that being the more standard approach, to get current, transmission, and conductance. Now, just to describe how this kind of works, typically with these sorts of calculations, if you wanted to do them, you would need to purchase very specialized software or pay a student who probably isn't qualified to set that up to build your own, right? You have to pay an outside company, or you'll need to have, hire a specialized student or a student who just isn't that knowledgeable graphical interfaces. With Maple, you get that by default. So we're able to make a complex calculation, which does 5 different steps. It builds a junction. You can import the geometry. It has to import the geometry, and then you have to choose your simulation settings, usually your transport simulation. Use your electronic structure theory to get your quantum chemistry results, so you know where the electrons are and where they're flowing in our system. And then you have to send that data to an external calculator program. And although not always important if you're working with grad students, if you have undergrads, plotting the results is always a very handy thing. With our worksheets, we've managed to reduce this to 2 steps. You build a junction, you import it and choose your simulation settings, and the worksheet does the rest for you. So I want to do a quick application here because, of course, we want to see what this can actually do. And the application here is based on tunnel current RNA sensors. The idea here is that you have a molecular junction-like setup where you have 2 electrodes and you run a molecule between them instead of attaching it. And the idea being, as the molecule runs between the gap, you get a current flows. And if you can look at variations in that conductance, you can identify the different nucleotides right here. And the idea being, this is a much more rapid approach to sensing, well suited for short-lived RNA strands. And as shown by this group out in Colorado Boulder, though, you can actually also identify multiple peaks and even draw these back to different orientations of these nucleotides. Although, if you might notice how close they are, this is a complicated problem because, of course, many of these peaks are at about the same conductance value. So you would basically say at a fixed voltage, you would get about the same current, meaning they're hard to separate and it's very fine difference. So we need to get a very fine description of the peaks. So we took a look at this with an undergrad student of mine, and we used a relatively simple model at this point, which we're hoping to scale up to just sort of test, like, can we tell a difference between our methodologies using aluminum electrodes? Because at the time when this work was done, it didn't have support for gold at the time, which was the standard thing that the actual experiment here used. So with that, we looked at RDM on the left and more standard DFT methods on the right. A few things we noticed: the RDM, again, predicted a much lower conductance. The DFT predicted a higher conductance, but also both predicted a different ordering, right? With your uracil being the lowest conductance, then your cytosine, and then guanine at one point, but then switching to adenine at another. Whereas in the case of the DFT, you're getting uracil, then adenine, cytosine, then guanine. Now, that does say we get a different ordering. That's telling me I'm at 10 minutes. And at this point, we wanted to look and say, well, what if we could scale it to gold? How did that make a difference? Well, recently, in the last year or so, the QC Toolbox added better support for handling heavy metals like gold. So now you can do metal-centered calculations or metal electrode calculations. So we took a look and we looked at how the patterns would change if we actually put in the proper gold electrodes. And we had a good and a bad, I guess. We looked at the DFT one right here. The RDM stuff is still ongoing. And we found that experimental, on average, even though the peaks are not all at this exact line, they're all right around this line right here. So we found that, hey, we actually do match up pretty closely in that. But what about the ordering? We actually found that no, DFT didn't, although it did in this case almost get lucky and get very close, it actually did mess the ordering up some. Right? We found that this adenine should have been probably at the bottom, and here it is right at the top at the highest conductance. So we still have a bit of an issue. And a reason we think for this might be is because, well, if we look back at these peaks from the experiment, right, we see that they have multiple peaks, each of these corresponding to different orientations, right? So the student I had work on this as being an undergrad mostly did one orientation or one or two. Right? So it's very possible that we need to look at more orientations, and probably exactly, and also improve electrode description to get the ordering exactly right. Although it is nice that we are getting relatively close, at least with a very simple description. So with that in mind, where is this kind of going, right? We're looking here to move on to not only using our traditional RUQT, but we've also developed a new code called PyRUQT, which is just the Python version. It uses different NEGF or transport calculators in order to do larger electrodes, which now fully repeat out to infinity, or called semi-infinite, where you can sort of make approximations to simulate them going out to be infinitely long electrodes. We hope this would actually improve the description and hopefully the accuracy of the results. And we want to, now that these things are getting integrated, we want to revisit this RNA sensor problem with new students who are going to be taking over the project and looking to see, hey, can we get the ordering right if we improve the transport description? And that's basically where the project stands right now. Hopefully have some more. And I just wanted to say that's all I have for today. I've got a few more slides and stuff to show off, but I'm pretty much out of time as I understand it. Yes. And I want to just thank a few of my students, Don and Matt. Matt, Justin. Matt's the current one helping out. Jason, who's the one who now is gone to private industry, but he's the one who did most of the nanoelectrode work, as well as some of our sponsors, although only Exceed was part of this particular work, and they now don't exist anymore, being replaced by a different program. The NSF and the PRF have both offered their support to continue this kind of work going forward, particularly the PRF, except for the context of petroleum derivatives, as well as my collaborator who's helping with the development of another method, which is not based in the QC Toolbox, that I also hope to integrate with Maple in the near future. And if you're interested in any of these codes, that's for that. They're all available on our group GitHub, which I can put in the chat or a link to anyone who would like to use these methods, including some of the approaches that I've used today. And I think I'm out of time, right?
Yes, thank you very much, Erik. That was a great presentation, and it tied in very well with the presentation we had yesterday in the Maple and Education session, which actually introduced us to the quantum toolbox. So thank you very much for tying the two together. That was great. At this moment, I'd like to invite anyone to please unmute themselves and ask a question. Don't be shy. But if you are, then feel free to type the question into the chat, and I can read it out as well. So please, yeah, go ahead, Jason.
Yeah, Erik, thank you very much. I think this was a great talk for me. At App State, there's a couple of people that do density functional theory, and I had a student tried to explain this stuff to me. You far exceeded his explanation, so I thank you for that. Can you tell me a little bit more about what's in the GitHub? Are they Maple files, or because I think some of the people here use Mathematica, so I would definitely like to pass this on to them.
Oh, yeah. So at the moment, it's workbooks. Actually, I can kind of, the other thing, let's see if I can close this presentation for a second in slideshow. I actually can show this is the workbook right here. So this is the DFT one. And what I try to do is, because traditionally, I've only recently taken PhD students as my university grows. I basically try to set it up so that you load the toolbox and you put the specific settings. And of course, I have it nice and tutorialized. And then it actually will run the code down in a code block down here. But in the GitHub itself, right, and I will upload the workbooks that I used to make the stuff today down here. I have I've just been uploading the workbooks to GitHub for now. I'm looking to see if there's another solution in the future, but also the supporting codes you would need to run these calculations being also right here. Right, so I have both the supporting codes, including what we want to integrate in the future right here. And then you would download the workbook, you would get the transport code that goes with it. And then you will need the toolbox, which is part of Maple. But if you have those three things, you can actually do the calculations. And these are all, this of course is free. Both of these are available freely.
All right, that's great. If there are no more questions for Erik, then we will move on to our next presenter. So thank you very much, Erik, once again. And with that, I'd like to welcome Samir Hamdi, who will be presenting on new Gauss hypergeometric solutions to the quartic equation and summation identities of reciprocal of first derivatives of polynomials. So welcome, Samir, and please go ahead.
Hello, good morning, everyone. Can you see the screen?
Yes, we can. Thank you.
Okay, so today I'm presenting new Gauss hypergeometric solutions for the quartic equation, and as well summation identities for the reciprocal of first derivatives of polynomials. I will. Okay, so this is the outline of the talk. So I will present how we derive the solutions based on the Gauss hypergeometric solutions. And also the second part would be similar to the Newton polynomial identities and Vieta formula for quartic polynomials. We discovered that there is new identities related to the reciprocals of the first derivatives of the roots. So the second part is actually general, so not only for the quartic, but for any polynomial of degree n. But today I will focus on for the quartic equation. So I will present briefly how we derive the Gauss hypergeometric solutions for the quartic equation. As you know, like for polynomials according to the Galois theory, so there is no general exact solutions beyond the quartic that's based on radicals, and that's the Abel-Ruffini impossibility theorem. So, however, beyond the quartic, it's still possible to find exact solutions based on integral methods, hypergeometric functions, Jacobi theta functions. This is possible. And also for the quartic equation, we know that there is a hypergeometric solution for the quartic trinomial. However, the novelty of the work today is to present the general solution for a quartic of all coefficients with all terms. And also with a low order hypergeometric function, which is the Gauss hypergeometric function. So we'll present this fundamental solution. The basic idea for the solution is to use a cubic resolvent. And for the cubic resolvent, we use for the depressed cubic resolvent, we use a Gauss hypergeometric function that will will be used to derive the general solution for the Quartic equation. And as well as I mentioned, I will present the identities for the summation of the reciprocal of the first derivatives of the Quartic evaluated at the roots, at the 4 roots of the Quartic. So this is the general idea. So the Quartic is a classical equation. So although this is very classical field, still there is possibility to find new solutions or new forms of the solutions, and as well implementation in computer algebra system like Maple. So the basic idea is we write the Quartic as the product of 2 quadratic trinomials. And when we expand the left hand side, so the coefficients G1, G2, H1, and H2 are defined as you can see here. So G1 plus G2 equal A. The product plus the sum is equal B. And G1 times H2 plus G2 times H1 equal C. And H1, H2 equal D. So very important for the third equation in the system here will be used for the coefficient C to find the expression for the cubic resolvent. So the next step is we introduce a new variable y equal h1 plus h2. And now the system reads in this following form. So I will read it for you. So G1 plus G2 equal A, G1 times G2 equal B minus Y, and H1 plus H2 equal Y, and H1 times H2 equal D. So using the Vieta formula for this system, we can write the 2 subsidiary quadratic equations. As you can see, G squared minus AG plus B minus Y equals 0. And the H2 plus YH plus D equals 0. So what we do with Maple, we solve this system of 2 quadratic equations, the subsidiary quadratic equations. So we use the Maple command solve, and we solve the first equation. So we issue the command solve G squared minus AG plus B minus Y. We solve it with respect to G, and the same thing for H. So we solve that quadratic equation, and we find these classical 4 solutions, G1, G2, H1, and H2. However, in this solution, we don't know the value of y yet. So y is not known. So we are not done yet. So next step is to use, I go back here, you see like in the system here at the bottom. So G1 times H2 plus G2 times H1 equals C for the coefficient C. We did not use it yet. So what we do is we simplify that expression, and we plug the value of G1, H2, and G2 and H1, and we find this expression for the coefficient C in terms of this radical. So the trick now is to take C minus A times Y over 2, and we square from both sides, and we get rid of the radicals, and we obtain the cubic resolvent for the Quartic equation. So what we mean by the cubic resolvent, it means that once we solve the cubic resolvent, we find y, and once we find y, so we get back substitution, and we find the coefficients, and we find the solution of the Quartic. So the idea now to solve this cubic resolvent, this is a very interesting idea, is to use a very careful change of variable z. Z equals simply y minus b over 3. And if we use that change of variable, and we can depress that cubic to this form of depressed cubic, and we can use the cubic resolvent to make the calculation easy in Maple. And we find finally the expression for the cubic resolvent, which reads z cubic minus b times z minus a squared plus c equals 0, where b and c are the coefficients given by the expressions, as you can see here. Now, the next important step in the solution is we express the solution of the depressed cubic resolvent using this solution based on the Gauss hypergeometric function. So this is very interesting because this is one of the compact and simple expression for the solution of the cubic based on the Gauss hypergeometric function. So it reads like Z, the solution is equal function. So unlike the solution of a cubic with radicals or with trigonometric functions or hyperbolic functions, like inverse hyperbolic or inverse geometric or radicals. So this solution is a beautiful solution based on the Gauss hypergeometric function and reads as you can see in this expression. The good thing about the Gauss hypergeometric function is a function that now is available in most software, like in MATLAB, in R, in Mathematica, and Maple, and also it has nice analytical continuation. So it's robust and is convergent. All the software takes care of the convergence. So there is no issue for convergence for this Gauss hypergeometric function. Now we do a back substitution now for the quadratic subsidiary equations, and we can plug the value now of Z of the Gauss hypergeometric solution of the cubic resolvent in these two quadratic system. And in the next step, now we find the value of G1 and G2, H1 and H2, all of them expressed as a function of Z. And remember, Z here is the solution of the cubic resolvent, and the nice solution based on the Gauss hypergeometric function. Now, the last step now, the quartic equation, so the polynomial of order 4, which is written as the product of two quadratic equations, product of two second order equations. We find the 4 roots of the polynomial, x1, x2, x3, and x4. And these are simple expressions, and where the G1, G2, H1, and H2 are expressed in terms of Gauss hypergeometric functions. So I think this is new. I haven't seen this solution in the literature, although it's a classical field. The good thing now we have general solution of the quartic equation based on the Gauss hypergeometric solution. You may know that for the quartic trinomial, there is already solutions based on the hypergeometric function F32, but this is the first time it's presented in this compact way based on the Gauss hypergeometric function. Now I will talk about the second part of my results that I obtained for the quartic. So this is related to the derivative of the quartic solution. So if we consider now, I will extend the Vieta and Newton formula by deriving new identities for the sum of powers that involve the reciprocals of the first derivative. So these identities are actually general. So, but in this case, I present them only for the quartic, but they are general. So for any polynomial of degree n, the identities that I will present in the next page are general. And so we consider the derivative of the polynomial, but evaluated at the roots x1, x2, x3, x4. And this is the expression of this identity. So this is the first family of summation identity. And I'm not aware, I haven't seen these identities anywhere in the literature. I present them here for the quartic, but these are general. And I have the general proof for based on two methods, either the Cauchy integral formula involving complex integration over contours, or using divided differences. Or the third way is a brute force. We can use just Maple, and we plug the values of x1, x2, x3, x4, and the derivative of the polynomial, the quartic, evaluated at x1, x2, x3, and x4. And it reads, as you can see on the screen. So these are 4 equations, and from the right-hand side is expression expressed as the coefficient of the polynomial. It's very similar to the Vieta formula, but it's really different from the Vieta formula or the Newton identities. So this formula is for the x1, x2, x3, x4, the 4 roots. But this formula is valid when the roots are distinct. So x1 should be different from x2, different from x3, different from x4, and of course for non-zero solutions. So the the second family of harmonic summation identities for the reciprocal of the first derivative of the roots, using Maple as well to prove it. As well, we can use divided difference or the general Cauchy integral theorem. So it is, as you can see here, and it's the 1, 2, 3, 4, 5 equations. And from the left-hand side, so you have the, it involves the first derivative of the polynomial. And on the right-hand side, it involves the coefficients of the polynomial, similar to the Vieta formula. And the last summation identity is as the following. So the second derivative of the polynomial evaluated at the roots divided by the first derivative. If you do all that summation, you will be identically equal 0. The same thing for the third derivative, and the same thing for the fourth derivative. So I did extensive research to really, I cannot claim right away that this is new because I haven't seen it, but this is classical field. So if anyone have seen similar expressions, I would be very interested to know that. Now,
hi Samir, we're
yes.
just a note, we're getting very close to the end of the time.
I'm finished.
So,
So this is the conclusion. So to conclude, so two things. We derived a new Gauss hypergeometric solutions using Maple for the Quartic, and also the polynomial identities. And the application are really is kind of solution looking for a problem. So this is kind of the applications like for the traveling wave solutions for the neuroscience or in hydraulic engineering, and also very important for the solution of the boundary value problems. So the direct application of these summation identities is instrumental for the derivation of exact solutions of fourth order boundary value differential equations with discontinuity jumps of the third derivative. So this is the end of my presentation, and thank you for your attention. If you have questions, I would be very interested to answer them.
All right, thank you very much, Samir, for this presentation. It's always nice to see content on the hypergeometric functions in Maple. At this time, I'd like to invite anybody in the audience if they would like to ask any questions. I see that we have some notes in the chat. Cyril is wondering maybe if you're familiar with the work of Harley and Cockle on this topic. Can you speak to that, Samir?
I think for the hypergeometric solution is known, but for Gauss hypergeometric solution for the Quartic, I think it's new, and also for the identities, I think they are new. So one of the interests in this conference to have the feedback of people and before publishing a paper. So I would like really to make sure that it's I'm not really doing something already done. But I think it's still there is room for you know, for with these classical equations to do something new.
All right. Thank you very much, Samir. If there are no more questions, then we'll move on to the next speaker. Just a heads up that we had one cancellation today. So our next speaker will be Felipe Tabera. And together with his colleagues that maybe he can introduce, he will be presenting on handling a cube through Maple and GeoGebra. So please, Luis, welcome, and please feel free to share your screen now.
Yeah, okay. I'm still seeing Samir screen.
Samir, maybe if you could exit screen sharing, please.
Okay. 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 I'd like to put myself. Okay. Well, thank you very much for the invitation. The idea we are working with our colleagues is just to how to work on either a computer algebra system or dynamic geometric software linkage. So we have like a test bed, just the cube. So this is the object we want to modelize. And this construction is very nice because it allows us to just work on it, just to study, for instance, degenerate positions, and just we have a set of nodes on the space, we have a set of links on the nodes, and we want just to explore how it may move, what's the whole space of configuration of this object. So when we start to trying to modelize, then we try first with GeoGebra. GeoGebra is a dynamic geometry software. Can you see my screen?
Yes, we can. Thank you.
And the main problem with GeoGebra is that if we try to do just naive configuration that resembles the cube, the problem is that all this type of software work on guided on a construction that has some inputs and then develops other linkages. So in this case, for instance, we have constructed starting from point A and just constructing some spheres and points at distant one. We can represent the cube, but the problem is that the dynamic of the cube is quite not good. We can see that at some point, even if we have some physical configuration that are attainable, the software is not able to find it. And also the movement is weird. The problem with this kind of construction is that, for instance, we cannot see it, but this node here can only move in one dimension. While, of course, in our physical construction, we can work it in more dimensions. Of course, the problem is that if we change the point of view and then we try to reconstruct the cube starting from a different node, it involves a lot of computation. So it's a non-trivial problem how to construct this object on this kind of software. So what we tried to do then was, okay, so just take a construction of the cube. Okay, I will share the full screen, that will be better. Okay, let's try to represent in Maple the cubic linkage. Then we have 12 nodes, we have 12 links, so of course the dimension of the full space of configuration should be 12. And when we try to do this, we just get no output. And this is not a problem specifically with Maple. This is just really a very simple problem that is really a benchmark problem that it's really hard to compute this dimension. So we say, okay, so let's just fix some other nodes. Let's say that, for instance, one of the node will be the point 0, 0, 0. Another node will be the point 0, 0, 0, 1, 0. And then we choose another node and we fix a plane it will belong to. The problem with this transformation or with this restriction is that, of course, now when we do this, once we have fixed two nodes, O and U, okay, I fix these two nodes, and then I say, okay, this third node will be on the same plane as the other one I'm having here. So I will have here in this plane, but the configurations that just turn around the axis really provides us different configurations that we cannot just, we can, how can I say this? We can restrict our general configuration to this restricted one in more than several ways. And algebraically, this will mean that we will have several algebraic components. Also, we could try to construct this dimension of this linkage purely by some geometric considerations, but we try to do it purely algebraically in order to be able to extend it to other configurations. And the thing to do this is, of course, we try to work with a quadrangle, and this can be precisely described. The ideal is correct. We can check which variables are free and which variables are algebraically dependent, but we cannot go to dimension 3. So we try to do this is just to describe some degrees of freedom for each vertex. In the original configuration I showed you in GeoGebra, we were able to do that, but we could not really work on the purely algebraically set. We always have to add some conditions. We always have to add some restrictions to our linkage in order to be able to the cube. And in fact, what we started to do is, okay, just delete point A. And with some effort, Maple is able to compute this dimension. We don't know if this configuration is irreducible. Of course, we can describe by geometric means that this configuration is irreducible, but we cannot really compute it. And started from this work, the thing is that whenever we have a linkage and we eliminate one of the points, then we can try to parameterize that point from the rest of the linkage, from the rest of the 7 nodes of the cube. And this is what we did here. We, of course, tried to work with a lot of cases. I think that we had around more than 60 primary components of the ideal. It's not something that we can really compute. We just classify them guided by some geometric insight, but we were not able to compute the full configuration. But at the end, we were able to prove that, of course, the ideal is not prime. The ideal have a lot of primary components, but the dimension is at most 6. That for the restrict configuration is the expected one. We also try to work with the difference between the real space of configuration and complex space of configuration. Our main tool was the polynomial idea library and the Grobner basis library that only work on the complex, but reasoning just in some factorization of polynomials that we can compute in the ideal and trying to write them, like, for instance, sum of squares, we were able also to deduce some properties of the real space of configurations. So this is like just a starting point on the most problem of studying linkage, studying rigidity on graph or configuration of points in the space. How can we translate this to good models of the cube? How from a concrete instance that even maybe degenerate, how can we choose the nice or good free variables that we allow us to construct the cube and also to be able to visualize it in a more dynamic way? So I will say that this is just like a start of a broader problem that computationally is quite hard, and we are still studying it. Here I can show some of the connected components of some degenerate cases that appear when we work purely algebraically done, but of course will have no geometric meaning. And I think that this is more or less all I wanted to say. Thank you.
All right. Thank you, Luis, for that presentation. Are there any questions from the audience for Luis? Please feel free to unmute yourself and go ahead. And in the meantime, I was just wondering, Luis, what other structures are you planning to study as part of this? And what are some of the challenges in extending this work to maybe a more complex structure?
I think that we were trying to study rigidity, and also we wanted to use this kind of construction as a test bed for automatic theorem proving in the context of geometry. And then in that case, we cannot really use this geometric reasoning that that allows us to compute the real answer. So the real problem is that how to study linkage, to study rigidity, to study movement, and to try to develop these tools in order to focus on a system that is able to say something to prove theorems on a geometric setting. That could be the further goal.
Okay, great.
I had a question. Luis, I work in engineering, and there's a lot of cases where automation and manufacturing has the similar sort of issues with inverse kinematic problems. Is there much interest in that crossover between transcending it from the geometry angle into the physical?
Yes, of course, that could be, that's for sure a quite challenging problem, but at the end, that's what we would like to know. Just like a set of restrictions on, just say, an industrial construction, to how to construct it, how to parameterize well, because different configurations will have different set of variables that will allow us better to represent the object or to construct the object. How to choose them? How to choose them when we are moving from one configuration to the other? Because during the path of the formation, we will have to change at some point the variables. That's yes.
Thank you.
Yeah, so that's what I was actually kind of wondering, sort of how do you decide which properties to model and which to leave out to sort of reduce the complexity?
I would like to know the answer. The problem is that, of course, for these kind of simple examples, we can visualize it. We have the geometric intuition. But how to formalize it and how to do it in full generality, except trying variables and seeing which work and won't. You are guided by the construction, but you don't have a full answer there.
All right, that's great. Thank you very much, Luis. Interesting presentation. And with that, I'd like to invite our final speaker for today, Bennett Palmer, who will be talking about construction of equilibria with symmetry for anisotropic surface functionals. So let's see if you can share your screen, Bennett, and go ahead, please. We can see your slides.
Can you see it?
Yes, success.
Oh, good. Okay, let me just move this. Okay, so thank you very much for the opportunity to speak here today. As the moderator said, I'll speak about construction of equilibria surfaces with symmetry for anisotropic surface functionals. And this is mainly an application, the Maple application I'm using is primarily involving computer graphics. So to introduce this, it's not. Okay, so in nature, what we see when we look around us is we see interfaces. So we see an object. When we look at an object has an interior and an exterior, and what we're actually seeing is the interface between its interior and exterior. So in this picture, we see two particular types of interfaces. On the left, there's a drop of water on a substrate. On the right, there's a crystal on a substrate. So they're essentially a pure material sitting on a substrate in some sort of environment. And of course, the shape of the interface is completely different. Okay. So if we ask why that's true, we have to go to thermodynamics. Thermodynamics tells us that the interface forms so as to attempt to minimize a particular type of potential energy subject to whatever constraints are imposed by the object's environment. So this potential energy, among other things, it will depend on the chemical composition of the object. For a liquid drop, which we saw in the previous picture, if we assume the drop is homogeneous, the energy is a constant times the surface area, the constant being the surface tension. Okay, so we get a rather homogeneous looking surface, we get a nice smooth surface. But for anisotropic materials, that is materials, for example, the atoms that make up the material could be in some ordered state, as in a crystal, the energy will be anisotropic. So in order to describe this energy, I've drawn here a surface, the surface normal, I've called this nu, and that encodes the direction of the surface. And the anisotropic energy of a crystal is obtained by taking a particular function, gamma of nu, and integrating that over the surface. Okay, and this is our anisotropic surface energy. And the function gamma of nu, we can think of nu as living in the two-dimensional sphere, which is where this normal will live. This gives the unit energy per unit area of a surface patch with normal nu and area d sigma. Okay, so this type of anisotropic surface energy was introduced by Gibbs in order to describe exactly what I talked about, which is the surface energy of an anisotropic material. So this sort of surface energy has a very important surface. This is called the Wolf shape. And what I'm going to give is this famous Wolf construction. So we think of the two-dimensional sphere, which I've drawn as being one-dimensional. And at each point, I've called the elements of the sphere n instead of nu in this picture. But at each point n, we go out a distance gamma of n, so that this vector is gamma of n times the normal. And then we take the hyperplane, in this case, it will be a plane in 3 dimensions, and we take that hyperplane and we take the components of that of space, which the hyperplane divides space into 2 components, and we take the component which contains the hypersphere and throw that contains the sphere, and we throw the other component away. Okay, so we do this at every point of the sphere, and then we take the intersection of all the half spaces that are left. And the boundary of that is what I'm calling the Wolf shape. So in this picture, the red plot is the plot of gamma of n times n. That's the radial plot of gamma of n. And then the green shape is the Wolf shape, which is what's left over when we do this construction and then take the intersection of the hyperplanes. Okay, so a very important theorem is what's called Wolff's theorem, and Wolff's theorem says that this Wolf shape is the absolute minimizer of the anisotropic energy E among all closed surfaces containing the same volume as the Wolf shape itself. Okay, in the isotropic case, that's when gamma we can take to be a constant, which we'll take to be 1. This reduces to the classical isoparametric inequality, which says that the sphere has least surface area among all surfaces enclosing the same volume. But in general, this is Wolff's theorem is a sweeping generalization of the isoparametric inequality to anisotropic surface energies. Wolf was a Ukrainian crystallographer who was particularly interested in the equilibrium shape of crystals and also in the growth of crystals. Okay, and this theorem essentially determines the shape of a crystal. Okay, so the subject of my talk is about equilibria, and besides minimizers for this type of energy, we're interested in equilibria. And by using the calculus of variations, we obtain that the equilibria are characterized by a certain invariant of the surface, which is called the anisotropic mean curvature, which I denote by lambda here being a constant. So this is equilibria with a volume constraint, that the volume inside is fixed. Okay, and maybe the quickest way to discuss this is using the generalized Young-Laplace equation, which is that a constant times this anisotropic mean curvature when we have a equilibria is given by the pressure differential, the pressure outside the surface minus the pressure inside the surface. Okay, so we're interested in constructing equilibria, which would be characterized by this lambda being a constant. So the construction goes something like this. So we imagine, we're going to imagine a wolf shape, which is our minimizer being axially symmetric. So I've drawn just the generating curve of that axially symmetric surface. And then this second curve is going to be a generating curve of an equilibrium. The coordinates here are called UV, and the coordinates on the curve that we're trying to construct will be called RZ. And these are related by we let the points correspond where their normals agree. So the condition for this curve to generate an equilibrium surface is that the horizontal coordinates of these two curves are related by a quadratic formula. Here, lambda is the anisotropic mean curvature, which is assumed, which we want to be constant. And the C is going to be a second parameter, which is called the flux parameter. Okay. And then the vertical coordinate of the generating curve is just found by integration. So here we would solve this quadratic R as a function of U, and then we'd solve for U as a function of V along this curve, and then integrate this to get the vertical coordinate. And this condition is just the condition for these normals to be parallel. Okay. So the surfaces that will result are called anisotropic Delaunay surfaces. The original Delaunay for surfaces for the isotropic energy were found by Delaunay in the middle 1800s, and those are important in determining equilibria for constant mean curvature. So the anisotropic Delaunay surfaces fall into 6 distinct types. There's the plane, which isn't very interesting. There's when lambda is equal to 0 and the constant C is not equal to 0 in that formula, we get anisotropic catenoids. We get when lambda is less than 0 and C is equal to 0, we get the wolf shape. When lambda is less than 0 and C is this given constant, we get a cylinder, which isn't very interesting either. And then when lambda is negative and C ranges through a certain positive range of parameters, we get anisotropic unduloid. And when lambda is negative and C is negative, we get a surface called an anisotropic nodoid. So some pictures of these are as follows. So here is a wolf shape, which is assumed to be axially symmetric. And then we get part of its anisotropic catenoid. Here we get part of an anisotropic unduloid. This is one period of an anisotropic unduloid. This surface extends to be an infinitely periodic surface. And here's part of its anisotropic nodoid. So I'll show you these surfaces similar to these on a worksheet in a minute. We'll get to move them around and see a little bit better. But then there's a construction where we can replace, in this we have an axially symmetric surface, and we can replace the cross-sectional curves, which here are circles, with some other convex shape. And if we do the same thing, so that will give us a new wolf shape, which corresponds to a new anisotropic surface energy. And if we do the same thing on the remaining anisotropic Delaunay surfaces, they will still be equilibria. And I'll show you that on the next slide. So here I've replaced the circles with this sort of more or less square shape, and these give anisotropic Delaunay surfaces for the surface energy with this wolf shape. So I'll show you this on a for some reason I'm not seeing the zoom controls on my screen. Oh, this is why. So on the worksheet, see, here would be a wolf shape. It has, again, starting with circular cross sections. Here's part of its anisotropic catenoid. Here is part of the anisotropic nodoid, but I've left it open so that you can see that inside the surface has self-intersections. And again, this is two periods. It would extend infinitely in both directions. And here's part of an anisotropic unduloid. This is one period. And you could see that the top would fit into the bottom, and this would extend periodically. And here's what happened if we replace the circular cross sections with hexagonal cross sections. Here's part of the, this is the wolf shape. This is part of the anisotropic catenoid. Here is part of the anisotropic nodoid. And here, this is the not, oh, there it goes. This is one period of the anisotropic unduloid. I have to go back to the reader. Okay, so besides this type of symmetry, which we started with rotational symmetry, the other type of symmetry we might have is helicoidal symmetry. And here this involves another construction. So I'll just basically talk this through. This starts with this wolf shape. This wolf shape is given by 1 plus small constant times the third component of the normal squared. So this that functional is what we integrate over a surface in order to get the surface energy. This curve on the right is what's called a treadmill sled. So this curve satisfies a quadratic equation like this. This constant mu2 depends on x. And this curve is rolled without slipping on a treadmill. So if we imagine rolling it on a treadmill, the origin will trace out a curve, which is this red curve here. This is the generating curve of a helicoidal motion. So this is a planar curve, and I've darkened in part of this, the curve that's in this picture. And then this is subjected to a helicoidal motion. It's rotated and translated vertically at the same time. And because of this equation, this will produce a surface with constant anisotropic mean curvature for this wolf shape, which is invariant under a helicoidal motion. And here's another example where we take a wolf shape, instead of being elongated in the vertical direction, it's sort of squashed down and it's shorter and fatter. Here's the associated curve. This is called a treadmill sled. This is rolled without slipping on a treadmill. The origin sweeps out this generating curve. And then part of that is this black part is subjected to a helicoidal motion, and it traces out this helicoidal surface.
Hi, Bennett. Sorry to interject, but we're running out of time. So if you could just conclude, and we'll leave some time for questions. Thank you.
Sure. So here's one more example of that, and I'll conclude here. And this is what I've talked about is the result of these three older papers. And yeah, thank you very much.
All right. Thank you very much, Bennett, for this presentation. I really enjoyed seeing some of the graphical representations. Are there any questions from our audience members for Bennett? At this time, please feel free to unmute yourself or type the question into the chat. And maybe I'll just start with Bennett. So your formulation uses a constant term for lambda. Can you speak to the extensions of a case where lambda is not constant?
Sure, that might occur when you have external forces, in particular, when you have vertical gravitational force, lambda would be a linear function of the height. And another case, which can actually be solved in much the same way, is if you have a rotating drop of an anisotropic liquid, something like a pneumatic liquid crystal, and when it rotates, there's a centrifugal force, and in that case, you can solve it in much the same. The lambda will be a quartic function of the distance from the rotation axis for like a spinning drop, and in that case, it can be solved also.
All right, thank you for that. Are there any questions from the audience for Bennett? Okay. All right, so I think, thank you very much, Bennett. That was great. And that basically concludes our session.